Okay, let's do area again. Again, this is going to be part two of the series of finding area. Part one, I did more examples, but I did everything with respect to x. I'm only going to do three here, but all of these are going to be with respect to y. And I just want to highlight the fact that the area here is always going to be the integral of right minus left dy. And what I mean by that is I don't care where you are in anything. It could be this curve and this quadratic. Okay? If you want this and you want to start stacking them this way, I don't care what quadrant you're in, all of these have positive x values and then these have negative x values. It doesn't matter. These x values are all bigger than these x values. So if you want to find this line, for example, and you want to find that distance, because that's the height of your rectangle, let's say this is like 2 and this is negative 2. If you do the right 2 minus a negative 2, you get 4, and it's going to give you this. It doesn't matter if it's 0. Look at this. 0 minus negative 1, let's say, gives you 1, which gives you this length. It doesn't matter where you are in the coordinate system. If you take the right curve and subtract the left curve, you will get this difference. This difference is the length that you need because this is the length of the rectangle. dy is the thickness of the rectangle. This then gives you the area of each rectangle and you sum them all up. And again, your bounds, of course, are y values. So with these three examples, I'm going to use this. Where on the other example, and again, you can look at the old video or part one. Part one was all these rectangles were all vertical. All the rectangles' heights were the top curve minus the bottom curve. Top curve minus bottom curve. It doesn't matter top curve minus bottom curve. You needed this length. Well, it was always the top versus the bottom when x was the thickness. Well, now I'm looking at y. All of these are going to be dy. Okay, and so when I look at any of these curves and I take the top or the right minus the left, I have it. So let's draw these. So looking at this first one, again, you're going to recognize these two from the first video. It's the same thing. I'm just going to do it in the other direction to prove to you that the area, obviously, hopefully it's obvious, that the area is the same. Now I'm going to stack these rectangles this way. So the thickness of each rectangle is dy. I'm going to sum them up from my y values, starting at a y value of 0 all the way up to a y value of 6. And I'm going to do the right curve minus the left curve. So the first thing you have to do is actually find the right curve. This equation tells you y as a function of x. The height of the function, well, we don't want the height of the function. We want this distance. We want the x coordinate. The x coordinate tells you this distance. So you have to solve this for x. So go ahead and take y equals 6 minus 2x. Let's subtract the 6 over. Y minus 6 equals negative 2x, and then divide by negative 2. So I get negative half y plus 3 equals x. This is the right curve. The left curve is just x equals 0, so we don't have to worry about that. Again, this tells you the horizontal length, the horizontal distance the curve is, based on any y value. So that's what we're going to sum up. So negative half y plus 3 is the length of each one of these rectangles, and the thickness is dy, and we're going to add them up from 0 to 6. Okay, so this is going to be negative y squared over 4, right? Follow the power rule, increase the power by 1, divide by the new power, plus 3y from 0 to 6. Plug in 6. Negative 6 squared, so negative 36 over 4 is 9, plus 18. Negative 9 plus 18 is 9. Subtracting, plugging in 0, but 0, 0, and see you later, 9. And if you want to review, it was still 9 in the last part. Think of this geometrically. This has a length of 3, this has a length of 6. It's a triangle, 1/2 base times height, 1/2 of 18 is 9, right? We can check it very easily with geometry, and we can compare it to the old integral. Again, it has to be the same area. It's the same as triangle. I'm just stacking rectangles vertically in this case. So I need an equation that gives me this distance. which is x equals instead of y equals when I stack them the other way. Okay, this one is an advantage. If you remember last time on the video, I had to stack them this way, and I had to do two separate integrals because here the top changed. But if you think about these rectangles, the right curve is always here, and the left curve is always here. So we actually don't even need to do two separate integrals. We do, however, have to solve for these in terms of x. So this guy, the left curve, if y equals the square root of x equals y squared. And over here, we just add x and subtract y, so we get x equals 6 minus y. And so how do we find it? Well, we're stacking, accumulating from 0 to 2. Again, don't go from 0 to 4, 0 to 2. We're stacking them from a height of 0 all the way up to a height of 2. The right curve, which is this, right? This distance, all the way to there is here. Subtracting this distance will give you the leftover, right? It'll give you the between. So we need 6 minus y minus y squared. Each of those rectangles have a thickness then of dy. So do the integral. 6y minus y squared over 2 minus y cubed over 3 from 0 to 2. Okay, plug in 2 here, so we get 12 minus 2 squared is 4. 4 over 2 is 2, so minus 2, and then minus 8/3. So that's 10 minus 8/3. So that's 30/3 minus 8/3, and that's 22/3. And you can look back on the other video and see that it has the same thing, right? Whether we do it this way or whether we do it this way, we're still going to get 22/3. Okay, here we stacked all the things vertically. We had to do two separate integrals. We integrated from 0 to 4 and then integrated from 0 to 6. We used x values. Our integrands had x's in them. The thicknesses were dx, our limits were x. Over here, on this example, we're having the rectangles go this way. Our limits are y limits. Our functions are functions of y, right? X as a function of y. So y is in here. And then our thickness of each one is dy. Everything has y. Y limits, y functions, and dy, because you're stacking them this way. Okay, these two have been choices. I mean, it doesn't matter which one you do. You could do top minus bottom or left, right minus left. Doesn't matter. Over here, though, well, this one's a little different. What if I have this sideways parabola, x equals y squared minus 4y, and then I have the vertical line, x equals 12. And I want to find the area bounded by those two curves. Well, the first thing you want to do is you want to establish that intersection point. Okay? And so the intersection point that we're going to be concerned with there is 12 comma 6 up here. And again, take some time to figure that out. 12 comma 6, right? If you plug in a 6 for your y value, 6 squared minus 4 times 6 is 12. So 12 is x when 6 is y. Right, that's what we want. We need an x value of 12. We knew that's the intersection of this curve and this curve. And then down here is actually, oh, what is down there? Negative 2. Negative 2 and, oh, my bad. I screwed that up. 12, comma, negative 2. Okay? So that's probably the hardest part of this whole thing, and then being able to graph that. And then we're going to stack these rectangles like this. Okay, and then what we're going to do, we're going to accumulate them from a y value of negative 2 up to a y value of 6. We're going to take the right curve, which is x equals 12, minus the left curve, which is y squared minus 4y. We're going to make sure we use parentheses around that. Okay, so again, right curve minus left curve. This curve minus the parabola gives you this distance, and then you sum that up. Okay, and if you go ahead and do that integral, you're going to get 85.3. So 85.3 is this area, and it turns out that you can't actually do it with x. You know, this one and this one, you could have just done the other way if you wanted to, but in this one, you know, good luck trying to find the top curve and the bottom curve. It's really just the same curve wrapping around itself. So this is really the easiest way, and there's really nothing hard about this integral. I guess I could have done this integral for you. This is just 12y minus y cubed over 3, and then that's going to be a plus 4y, which is really just plus, what, 2y squared? From negative 2 to 6. And we can plug in 6 and get a monster value, subtract, plug in negative 2, and then you get that. You guys can do that one without me right now. I'm going to lose a little space. But here are 3 examples of doing right minus left. You can see the advantage of this one. You only have to do one integral, which is right curve minus left curve. This is just an easy example where we can kind of prove that it works. And this is an example that you couldn't do the other way. You have to do right minus left. But most of the time, you're going to do top minus bottom, because most of the time our functions are y as functions of x. This particular one, I gave you x as a function of y, meaning I'm giving you the horizontal position as a function of the vertical position. And so you can notice everything has to do with y. Y limits, right minus left, these functions right minus left are in terms of y, and then the thickness of each rectangle. Again, when you're thinking about every rectangle, we're looking at this particular really, really small rectangle right there. We're going to add up all those rectangles, right? The thickness of this rectangle is dy. The length of the rectangle is just 12 minus this curve. It doesn't matter if it's this rectangle or this one. It's always going to be right minus left. All these are going to be y's. dy from a y value to another y value.